All right, hi everybody. We are going to do the 11-1 notes today, but I'm going to start with the 10-7 homework since I haven't been able to touch base with you guys about that. Since your homework was to watch the video notes and do the homework. So 10-7, the main thing from 10-7 is you should be able to take two vectors, determine their dot product, and determine if they are orthogonal or not. And orthogonal is just another word for perpendicular. So make sure you guys are checking your answers. I'm not going to go through all of these. As I said in class, I wanted you guys to skip number 7 for now. This one, I'm going to cover a problem in a few minutes, and then I want you to go back and complete number 7, and then turn this worksheet in before you leave today after you watch the finish these notes on 11-1. So I'm going to finish one last problem in your 10-7 notes so that you can actually do number 7 on the homework. Before I get there, I did anticipate questions on the back of this worksheet, so I'm just going to cover one problem, and that would be number 9 on the back of this. So looking at number 9, it's telling us to determine the measure of the angle between two lines. So we didn't talk about finding the measure of the angle between two lines, but we can represent two lines as two vectors in component form and then just apply the formula that we have for the angle between two vectors. Okay, sorry, I cannot, for some reason my eraser is working, so I can't erase that mark. Just ignore that. Let's jump into number 9. So we have two lines that we want to find the angle between, but we are going to now represent these as vectors in component form. If you remember vectors in component form, they always start at the origin, and let's just say I have a vector like this. That ordered pair that represents this vector, let's say it's -2, 5, those two numbers, -2 and 5, indicate the slope of this vector if I'm talking about it in terms of being a line. So this means that the change in y is 5. Oh, hold on. Is 5, and the change in x is -2. So that vector right here has a slope of -5/2. So, and that should make sense over down 5, right 2, or up 5, left 2. So we're kind of going to go backwards now in number 9. So right now we're given this line, and we know that it has a slope of 1. So if we've got a slope of 1, let's think about what kind of component vector would represent that. That would be up 1 over 1. So back up here to my drawing. That would have a vector in component form of 1, 1. And then this line right here, y equals -4x, we know that has a slope of -4. And if we're thinking about this in terms of rise over run, it'd be -4 over 1, which means this component form of a vector that could represent that line would be x is 1 and y is -4. So that's how we would represent these two lines, the slope of these two lines, using component form of a vector. And the reason we do this is because to get the angle between it, all we need to really look at is that little space where those two lines intersect, which is why we're just talking about the vectors that can represent their slopes. Now that I have these two vectors that represent the slopes of our two lines, we can go ahead and apply the formula for angle between a vector. So cosine theta equals dot product. So that's going to be 1 times 1 plus 1 times -4, so 1 minus 4, all over the product of their magnitude. So the magnitude of my first one is the square root of 1 plus 1, which is the square root of 2, times the square root of the 1 squared plus 4 squared, so 17. So we've got cosine theta equals -3 over the square root of 34. And all we do now is plug in inverse cosine, type in our fraction there, and you should get that theta equals about 121 degrees. That should make sense too, because I'm going to move on down here and just use a little bit of space, because if we're talking about these two lines, x plus 9, so that is a slope of, I'm going to do x plus 9 in green, let's say that's 9, a slope of 1, and then we've got negative 4x, a y-intercept at 0, and a slope of negative 4 is going to look something like that. So that angle between the vectors, it says 121 degrees, that's what our answer was. And even just a quick sketch of these two lines shows about an angle of, that looks, you know, it's greater than 90, maybe greater than 100, which should make sense because it's close to 121. All right, so now let's move on to the final question from the 10-7 notes. So please get that notes packet out and turn to number 8. Okay, looking at number 8, I skipped this one in the original notes because, or on the last video notes, because we were just brand newly exposed to angle between vectors. So I wanted you guys to get some practice on the homework before we jumped into this problem. Finding all plane vectors orthogonal to another vector that have a specific magnitude or length. The fact that we're looking for all vectors orthogonal to this vector, think about how many possible answers that would be. The amount of vectors orthogonal or perpendicular to that. However, we are specifying that they have an exact length of 10 root 2. So that's going to be that parameter that kind of narrows down our options here. So if we think about the vector 6, negative 2, and we visualize it, just so you guys know what this problem is asking. So let's say we're over 6 down 2. We've got a vector right here. We want all the vectors perpendicular to that. Thinking about what perpendicular means, you now know that this would mean we want it to be at a right angle, but we want it to have a very specific length. So this would be one option going in up this positive direction. We could have another perpendicular one in this negative direction. Both of them are perpendicular. So this should help you realize we're actually going to have two answers for this because there will only be two answers that have the exact length of 10 root 2. So how do we find those two possible vectors that are orthogonal to 6, negative 2? We're actually going to use a system of equations for this because each of these two things, this being the first one, and the length of this, those will give us two equations. So being orthogonal, so first of all, find all plane vectors. So we are looking for all vectors in the form of x, y, and they're orthogonal to 6, negative 2. If that's true, then x and y, whatever that vector is, when it's orthogonal, that means their dot product has to equal 0. So this fact alone tells us, gives us this equation. The dot product would be 6 times x plus y times negative 2, so negative 2y equals 0. So right away we have this linear relationship between x and y if it's going to be orthogonal to 6, negative 2. So this is our first equation. Now we're going to move over to this fact that we're looking for a specific length of 10 root 2 because that will give us our second equation. Okay, so if we're told, I'm going to put a little line here because I'm working on the second part now. If we are told that our vector, remember we're just calling it xy, we are told we want that to have an exact magnitude of 10 root 2. Well, we know how to find the magnitude of a vector. It's the square root of x squared plus y squared. So now this means we've got a second equation that relates x and y. It's that the square root of x squared plus y squared equals 10 root 2. So we've got these two equations, also known as a system of equations, and we can use substitution here in this blue one, plug it in for one of the variables here, and work towards finding the possible values of x and y. So let's start simplifying this one on the right. So in the process of solving for x or y over here, it would make sense to square both sides of this to get rid of this square root. We end up with x squared plus y squared equals 10 root 2 squared. So we're squaring 10 and we're squaring the square root of 2. So that would be 10 squared, which is 100, times the square root of 2 squared, which is 2. So we end up with the equation x squared plus y squared equals 200. And we also have this equation on the left, 6x minus 2y equals 0. So this one on the left would be the easier one of the two to solve for x or y to make the substitution back into the equation on the right. So on the left, we've got 6x minus 2y. It doesn't matter which one you solve for. Let's say we want to solve for y. I would add 2y over to make that positive. Divide both sides by 2. And we've got y equals 3x. Now that I know y equals 3x, all we have to do is take that information and we can just plug it directly in for y right here. So now we've got x squared plus 3x squared equals 200. X squared plus 9x squared equals 200, which means 10 squared equals 200, or 10x squared. Get some more space down here. Okay, so divide both sides by 10, and we have x squared equals 20. So now we get two possible solutions for x when we take the square root of both sides. We get x equals positive or negative root 20, which is positive or negative. Since root 20 is the square root of 4 times 5, that 2 comes out. So here are our possible values for x. Now that we have these, we go back to y, and we need to find our possible values for y. So when x equals positive 2 root 5, y would equal 3 times, I'm going to write positive 2 root 5. Y would equal 3 times that, which is 6 root 5. Or y equals, if we have a negative 2 root 5, y would equal negative 6 root 5. So all vectors, let's go back to the original question here. This was asking for all vectors, all vectors that are orthogonal to this, 6, negative 2, which is where we got our first equation, that have the magnitude or length of 10 root 2, it's where we got our second equation, use substitution. We end up with two possible vectors that this will work for. So our final solution here, you scroll down. Our final solutions are 2 root 5, comma 6 root 5, and negative 2 root 5, negative 6 root 5. So this problem, this type of problem is pretty involved. The process should make sense, and you will need to practice it before it probably sinks in a little bit. But the number 7 on your homework is exactly like this. It asks you a very, very similar question, just gives you different values for the magnitude and the vector. So at this point, I want you to finish number 7 on your homework and turn that in after you finish these 11-1 notes. Okay, I'm going to skim through this first section here because I did cover this in class last week. And the reason I did that again is because it's hard to talk about 3D space on a two-dimensional platform. So it's just easier to describe what we're looking at here when we can move around in three-dimensional space rather than just referring to it on a flat surface. So 3D space is any space in which you need 3 numbers to talk about a specific location. So you need 3 numbers because you're talking about 3 dimensions now. We are so used to working on our XY plane, it's 2-dimensional. Length and width are the only 2 dimensions. So now what we're doing is adding this 3rd dimension. As you may remember from class, when we look at this XY plane here and compare it to this 3D XYZ plane, It's like we've taken our XY, that flat plane, we've laid it down. So it's now what I would refer to as the floor of this three-dimensional space. And the third dimension Z cuts right through it. So Z would be like if we're staring at the corner of a room, Z would be the wall going up and down, where X and Y now are kind of like the floor. In rectangular coordinates, we covered this already. Our third variable is Z already, X, Y, Z. There we can also talk about 3D space and spherical coordinates. We will not be focusing on that, but we can. And just like we had R and theta, there's a second rotation. We're not just talking about distance from the origin and then a rotation. Distance from origin, then a rotation, then another rotation, which we use with the Greek letter that looks like that kind of, called phi. Again, we're not really focusing on this. We are focusing on rectangular coordinates in 3D space. Plotting points in 3D space tends to be something that we think will be simple, but going through the process does confuse people. And I know I walked through this in class. I'll do it really quickly again. It helps to see some examples in person. But let's plot A and B and C here in number 3. So 2, 0, negative 3. Remember, that's giving us the X, Y, and then Z coordinates. So 2 on the x-axis. So the first thing you need to remember that the x-axis now is coming kind of through this YZ plane, and the x-axis is coming if you see the little red dot here, that movement is showing X growing larger. So that would be X moving in the positive direction towards us. And then back here, this would be negative values of X in what we're used to going left on the x-axis. That's now we're kind of going back on the x-axis into negative X space. So towards us is positive X. So when we see an X coordinate of positive 2, I imagine walking forward right here to where that little purple dot is. So I'm facing forward, walking forward. At that point, we've got a Y value of 0. So what that means is I've come forward 2. Instead of going up on the y-axis or down on the y-axis, I'm just going to stay there. And then the Z coordinate of negative 3 means, so this is Z, when we look at Z, up is positive, down is negative. So this is where you really do just need to practice and visualize this. Negative 3 on the Z-axis is right here. So but I'm already in, I've walked forward here. So now I kind of redraw this parallel line so it's parallel to Z, and then I visualize going down 3 on that. So that would be 1, 2, 3, and this would land me close to right here. So for point A. Or you can also, another way to look at it is go down 3 on the x-axis or the z-axis right here, and then draw another line perpendicular to the x-axis. So it's kind of these parallel lines, sorry I said perpendicular, these parallel lines help us visualize that third dimension. So the intersection here is where A would be, right there. Negative 1, negative 2, 4. So now let's do another one. Negative 1 on the x's. So now I'm going backwards. Here's my first movement back here, negative 1 on the x. Then I go down 2 on the y's. Remember, this being y, left is down. So I'm going to, from back here, I'm going down 2 on the y's. So parallel to the y's, I'm just going to move down. So negative 2 on the y's is here. If I draw a parallel line, then the intersection right here is kind of where I'm at right now before I move up or down on the z. So right now, this last little spot I drew, I'm kind of still on the floor. I went back 1 on the x, down 1 on the y. I'm on the floor still. And now for the z value of positive 4, I would go up 4 on the z's. So with this one, it's easiest, I guess, to just eyeball that. Going from here, I would go up 4 and land somewhere up here, B. The good thing about 3D space is the operations in 3D space mimic those in 2D space. You just add in this third variable z now. So distance to the origin should make perfect sense to you, and it shouldn't be a stretch at all. So when we talk about distance to the origin in 2D space, we call that r. We started calling it magnitude, distance, absolute value. That comes from the Pythagorean theorem, which is the square root of x squared plus y squared. That's how we always got it. Same thing. When you're talking about in 3D space distance from the origin, we're just adding on that third variable. So it's the square root of x squared plus y squared. Sorry, that is messy. Plus y squared plus z squared. So if it's from the origin, it's nice and simple. We just tack on that third distance to take account for. If one of the points in 3D space is not at the origin and you're looking for distance, we still apply the same distance formula that we did use in 2D space, which still comes from the Pythagorean theorem for distance formula. So the distance from P to Q, that would be just letters PQ equals the square root of, and then it's the difference between the x's squared. So again, this should sound familiar from Pythagorean theorem. So x2 minus x1 squared plus distance between the y's, y2 minus y1 squared plus distance between the z's, z2 minus z1 squared. This should look familiar from the distance formula. Now let's just do an example and get some practice with that. So let's sketch these 2 points and then find the distance between them. So A is 4, 3, 0. So on the x-axis, I'm coming forward 4. 1, 2, 3, 4. So coming forward on that floor of the xy axis, and then up 3 on the y's. So if I go up 3 on the y's right here and draw a parallel line between the x and y planes, this helps me visualize I'm standing right here on the xy plane right now, that floor. So that is out 4 on the x's, up 3 on the y's, and then z is just 0. So my final point here for A is just right there on that xy plane. So that would be A. And then B is 1, 3, negative 5. So 1 on the x's, negative 3 on the y's. So 1, 2, 3. Again, I'm going to draw a parallel line between, so I can kind of visualize where on the floor I would be. This is where I would be right now, going out 1, positive 1, x, negative 3, and then up 5 on the z-plane. So 5 on the z-plane is right here, but I'm actually counting up from right here, going up 5 vertically. 1, 2, 3, 4, 5. Those aren't always going to be perfect, but you should still be able to indicate pretty closely where that point is going to be. So that's B. Okay. So now we're looking at 2 points in space. I'm going to connect those with an orange line here. Here's our 2 points cutting through space, and we want to know the distance between them. So we're going to apply this formula up here that we just did. So their distance would be the square root of, now we take the difference between the x's. So that's going to be 4 minus 1 squared, add it to difference between the y's. That's 3 minus negative 3, so 3 plus 3 squared, plus difference between z's is 0 minus 5 squared. So we've got the square root of 4 minus 1 is 3, squared is 9. 3 plus 3 is 6 squared, is 36. Negative 5 squared is 25. Add those all up, and 45 plus 25 is 70. So the distance between these 2 points A and B is 70. Okay, the last thing, if we flip over to the next, is we're going to extend our knowledge now with our understanding of circles and their equations. And now we can extend that to a third dimension and talk about spheres and their equations. And it's going to look very close to the equation of a circle. So I'm actually going to put the equation of a circle right up here in this top margin to remind you guys. Hopefully you can remember. So a circle equation is x minus h squared plus y minus k squared equals r squared. So this is where you've got center hk and a radius of r. So now we're talking about a sphere with a center of A, B, C, and a radius of r. So we still talk about radius. It's the distance from the center of the sphere to the outside of the sphere. Drawing spheres is kind of hard. Let's talk about how to draw a sphere in 3D. So the way I think of spheres in a 3D space, so I've got my Z, my Y, and then X is going through it. So when we're talking about a sphere here, with the X and Y plane, I just visualize a circle with that. And then with the X plane coming out towards us right here, kind of visualize, kind of put this little line and this curve in front and then a dashed curve in back to represent that we're talking about a three-dimensional object here. So going back to the equation, it's going to look really similar. It's going to be x minus a squared plus y minus b. Instead of h and k, we've just got a and b squared plus z minus c squared equals r squared. So the only new thing here is we've got this third term, z minus c squared. So finding the center and radius of a sphere, we did problems like this with circles, and we're just going to tack on that third variable. So the way we did this with circles was we needed to organize my x values together, my y's, and my z's together. And then if you have forgotten, we are going to need to complete the square, which I know we had to review earlier this year, but hopefully that'll be a little more familiar this time. So when I rearrange these, I've got x squared minus 2x plus y squared. There's no other y term, so that would just be 0y plus z squared plus 10z equals 0. Okay, so we need each of these to be perfect squares. So I want my x terms to actually form a perfect square. Hopefully you'll recall that to do that, imagine building a square with these tiles. To finish in filling that perfect square, we would need to take this middle term, divide by 2, and then square it. So -1 squared, so to complete this square, we would just add 1. If I do that, I need to add 1 to the other side of the equation too. Then I want to complete my y squared, but my y is already a perfect square because the only term I have is y, so that would just be y squared. That's already a perfect square. Now I want to complete the z's to form a perfect square, so that would be z squared plus 10z. Now to complete that, again, I would take these 10z's, split them up, and then square it, and that would be plus 25. So I would need to add that to the other side. So now we've got all of this equals 26. So now I'm going to rewrite this as the factor x minus 1 squared plus y minus 0 squared, which you could just leave y squared, plus z plus 5 squared equals 26. So now when we're talking about center of this sphere, it's centered at 1, 0, -5, and has a radius of the square root of 26. So these problems you can expect to see. You may need to practice that completing the square process again, but hopefully this time around it's a little more natural and you can remember that process as you go. We're going to stop here. Example 7 is exactly the same as example 6 that we just did. It just involves a couple of fractions towards the end. But you've got enough to work on the homework, the 11.1, 11.2 worksheet. Numbers 1 through 5 only. So your homework leaving here today is finish number 7 on 10.7 and the 11.1, 11.2 worksheet, numbers 1 through 5 only for now, 1 through 5. And then we'll finish 11.2 video notes next class if I'm still not back. And then your homework after next class will be to finish the 11.1, 11.2 worksheet. All right, guys. See you soon.